So, this is the third type of the continuity. Discontinuity will be, we call it as a discontinuity of second kind. Second kind. Okay. Now, what is this discontinuity of the second kind? When the limit of this left hand limit, right hand limit both does not exist. That is, a function f x is said to have a discontinuity of second kind at a point x equal to x naught if the left hand limit and right hand limit if left hand limit or right hand limit both left hand or right hand limit both do not exist. Okay. They are definitely, and left hand limit do not exist, right hand limit do not exist. In fact, so neither left exists nor right exists. So, what happened that? For example, if we take the f x equal to say sin 1 by x. This we have seen already this function. What is the behavior of the function? If I look this function, here x, this is y, and just I am taking say here y is equal to 1, y is equal to say minus 1. Okay. Now, graph of this function, if you look the graph will be something like that. Say here something like this, is it not? And as soon as it comes here, it is very closed, very closed, and like this, but it never touches here. Okay. Similarly, here this is very closed. Okay. Very closed for this, and something like this, So, only at this means around the point 0 it gets so much congested, and frequently it going up and down very fast. That is, x near to x equal to 0, it has a sudden jump. At this point it has value 1, immediately in the nearby point it has a value minus 1. So, it has a sudden jump near at the point x equal to 0, in the neighborhood of 0. So, let us see, we claim that this x equal to 0 is the point of discontinuity of second kind. Let us see, suppose I take positive side. First you take x is greater than 0. Okay. Then if I take the number x equal to say 1 by 4 n plus 1 pi by 2. Okay. So, what happened this? Sine function we know, sine pi by 2 is 0. Then, because if we take the graph of the sine function, this is the graph of the sine function, sine 0 is 0, like this. So, sine 0 is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, and so on. But sine pi by 2, this is the point pi by 2, where it has a positive value 1. Sine of this thing 2 pi plus 5 by 2, that is 5 pi by 2, it has a 1 value. Then again this 3 pi, 4 pi, so it is 9 pi by 4 pi plus pi, 9 by 2 pi. Then this value, the function has a value 1. So, when it is pi by 2, sine of 3 pi by 2, sine of 5 pi by 2, and so on, the value of this is 1. And then if we look the sine 3 pi by 2 sine 3 pi by 2, this is our 3 pi by 2, this value 3 pi by 2, here it is 7, is it not? 7 pi by 2. So, 3 pi by 2 sine 7 pi by 2 and so on, the value is coming to be minus 1. It means when the point x, so 1 by x is this. So, x is very near, n is sufficiently large, the point is very close to 0. So, when it has the value n is the function. So, this function f x has the value 1 when n is equal to what? N is 0, n is 1, n is say 2 and like this, and equal to minus 1 when n is what? N is here say 3 pi by 2. So, we are getting n is equal to say if I choose the function f x, if we take x is equal to 1 by 4n minus 1 pi by 2, then the value of the function f x is minus 1 for n is equal to 1, n equal to 2, which 8 minus 7 pi by 2 and like this continue. So, we have a sequence of the point approaching towards 0 where the function has a sudden jump plus 1 to minus 1 and like. Similarly, in the left hand side. So, this function we said the limit of this function f x, which is sin x when x tends to 0 minus, that is limit of this sin 1 by x when x tends to 0 minus does not exist. Similarly, limit of this function f x when x tends to 0 plus does not exist. 0 plus 0 minus, here 0 plus does not exist. So, x equal to 0 is the point of discontinuity of second kind. So, this is what we have. There are some other also functions we can go at. Now, one more function we say that of course, this is not very important, but still we, if one or the more function at alpha is infinitely great, if either left hand limit or right hand limit is indefinitely great, means very large, it goes to infinity when this left hand or right hand limit goes to infinity, then in that case the function f, then f x is said to have an infinite discontinuity at the point x equal to x naught. For example, suppose I take the function f x, which is 1 minus x minus say x naught, okay, and the value of this at the point x naught I am choosing to be 0. Now, what happens if you take the limit of this function f x when x approaches to x naught from the negative side, then this is the same as 1 over x naught minus h minus x naught limit h tends to 0, is it not? Now, this is equal to what? This is nothing but tends to minus infinity, because this value will go to basically x naught cancel and h is sufficiently small. So, it goes to minus infinity, And when you go to the plus side, f x, when limit x tends to x naught plus side, where x naught, then what happens is limit x naught plus h minus x naught, and then h tends to 0. So, this will be tending to plus infinity. So, what is the left hand limit or right limit or any both of them, it goes to very large infinity, then point x equal to x naught is a point of discontinuity for this. Okay? Infinite discontinuity of this at x equal to 0. Okay. And then, so almost this we have covered. One is more examples which we can prove. The results, of course, without proof we can just say in the neighborhood of a point of discontinuity, in the neighborhood of the point of discontinuity of the second kind, the function makes an infinite number of oscillations. Because the reason is very simple. When you take the limit of the function either from the left hand side or right hand side, then you get a sequence approaching toward that function, where along a different sequence you have a different values. So, in fact, if x naught is the point of discontinuity of second kind, then we can get one sequence where the limit of the function will be say alpha 1, then another sequence will be obtained where the limit of the sequence is minus something, say alpha 2 or something. So, there is a sudden jump, makes an infinite number of oscillations. So, that is the case of this. Second is, of course, proof you can go through, that is very not difficult. The set of points of removable discontinuities of a function is countable. Okay. The reason is, proof is very like this. Suppose that S, if the set S, suppose the set S, which is the function, set of those function x, where f x has removable discontinuity, Okay. Let S be this. Suppose S is not countable. Then it has a component. Say B, which is dense in itself. Okay, that means a point alpha b is such that any is one side there. So, a point alpha we can find, a point alpha of the set B is such that in any, so a point alpha is such that in any neighborhood of alpha, on one side there are there are infinite number of points infinite number of points at which the functional values limits are all equal but are different from functional value at that point. Therefore, alpha is a point of discontinuity of second kind, which is a contradiction, because we have assumed the alpha as a point removable discontinuous point. Therefore, our assumption is wrong. So, the set S is countable. Similarly, another result is the set of points of ordinary discontinuity, that is discontinuity of the first kind, discontinuities of a function is countable. So, today we will discuss various types of discontinuities, and then we will see the relation between continuity and compactness. Compactness. Okay. So, let us see. First, we know a function f x is said to be continuous at a point x naught belonging to the domain say E, which is subset of say x d, if and only if limit of this function f x when x approaches to x naught exists and equal to the value of the function at a point x naught. Now, if this condition, when we are saying limit of f x tends to x naught equal to f x naught, it means the function must have a limit when x approaches to x naught, that is the left hand limit, right hand limit, both exist, they are equal, and the value of the function at the point x naught must coincide the value of the limit f x when x approaches to x naught. Then only the function will be said to be a continuous function. If any one of the condition fails, that is, if either the limit does not exist, that is the left hand limit of this function when x approaches to x naught from the left hand side different from limit of the function f x when x tends to x naught from positive side, then we say the limit does not exist at that point, or maybe if the limit comes out to be infinity for that. In that case, one or limit exists, but is different from the value of the function f x naught. So, when the limit does not exist, left hand right hand limit does not exist, then also the function will not be continuous, or if the limit exists, but its value is different from f x naught, then also the point x naught will be said to be continuous. Or it may sometime happen the limit of this function f x when x tends to x naught and y tends to y naught both does not go to mean left hand limit also does not exist, right hand also does not exist, then also we say the point x naught is a point of discontinuity. So, if this case is there, then x equal to x naught will be considered as the point of discontinuity for the function f x. So, obviously, the point of discontinuity depends on the cases whether limit exists, but different from x naught, then we name this point of discontinuity to some like a removable discontinuity. When the limit does not exist, then we give some other name to the discontinuity, or when the limit does not exist, left hand and right hand limit does not exist, we also give some other name, or sometimes the limit tends to infinity, then also we give sometimes different name. So, according to the situation, the type of discontinuities are characterized. So, first is let us see types of discontinuity. First is removable discontinuity. Removable discontinuity. Okay. So, removable discontinuity, if the function f x is said to have removable discontinuity at a point, say x equal to x naught, at a point x equal to x naught in the domain, if the functional limit, if limit of f x when x tends to x naught from negative side equal to the limit of this function f x when x tends to x naught from the positive side, they exist and both are equal, means left hand limit is the same as the right hand limit. So, limit exists, that is the limit exists. And second one is the functional value f of x naught also defined, is also defined, but the third is the limit that is limit exists. Third is limit of this function f x when x tends to x naught is not equal to the value of the function at a point x naught. Then we say x naught is a point of discontinuity and we call it as a removable discontinuity. Why removable discontinuity? Because we can redefine the function again, so that it can be the new function will be continuous, because the reason is this function can be redefined in such a way so that the new function becomes continuous. That is, if we define capital F x as our small f x when x is different from x naught and equal to the limit of the function f x when x tends to x naught, then the new function f x so obtained will be a continuous function. Then f will be continuous. F x has x naught as a continuous point. So, this function f in this where the x naught was not was a discontinuous point can be converted to a continuous point by simply removing or redefining the function. For example, if suppose we take the function f x is defined as say x for 0 less than equal to x less than half equal to 0 for x is equal to half and equal to say 1 minus x for x lying between half open at half close at 1. So, over the interval 0 1 we are defining the function. So, the function is of this type. This is 0. So, between 0 to half the function is a y equal to f x. So, it will be something like this. This is half, this is half, here is say half. Okay. And then at the point half it is coming to be 0. So, basically this half, this point is excluded. Here we are not touching half here, it is coming down, is it not? And then from this point when x is not half, just near to half, it start from here. So, we are getting this thing and then at the point 1 it is coming to be 0, this is 1. So, what we see here except at the point 1 the function is very smooth function. Okay. So, here if we look the limit of this function f x when x approaches to half minus, then this is the same as the limit of the function f half minus h, h tends to 0. From the left hand side you are approaching, from here you are approaching. So, take the point x is a half minus h. So, this is the point half minus h. Okay. So, consider this. Now, when the point is lying between 0 and half, the function is defined as x. So, this is equal to half minus h and then limit of this h tends to 0, which comes out to be half. So, from the left hand side the value of this limit is coming to be half. Now, from the right hand side if you look limit f x when x tends to half plus, then this is the same as to write limit h tends to 0 have f of half plus h, choose the point here which is half plus h and then approach about this side. Okay. So, when the point is lying between half and 1, this interval is taken in consideration where the function is defined like 1 minus x. So, 1 minus this and then take the limit as h tends to 0. So, this comes out to be half minus h and then h tends to 0 which is equal to half. So, right hand limit and left hand limit both are coming to be same as half. So, limit exists. Therefore, limit exists, limit of this function when x tends to say half exists. Okay. And equal to and equal to half. But the value of the function at the point half is 0, which is different from the value of the function at a point half, sorry, at the point half, because the value at the point half is given to be 0. Here we are limit value is coming to be half. It means this function has such a function where the limit exists, but the value of the function at that point is different from the limit. So, half becomes the point of removable discontinuity. So, x equal to half is the point is the removable discontinuity for this function f x. Okay. So, if we redefine the function instead of 0, if I redefine the function here, if I redefine the function here with value at x equal to half, then our function becomes continuous. So, that is why removable. Now, take another example, suppose another one. 2. Let us define the function f x as f x equal to limit of this as n tends to infinity cos to the power n pi x, where x lying pi x, okay, where the x lies between -1 and 1. Okay. It is not covering end points, open interval -1 to 1. Now, if we look the function cosine of this function, cosine pi x, when x lying between -1 to 1, the function phi pi x has the graph like this, -1 to 1. When x is 0, cosine 0 is 1. Okay. So, when x is half, pi by 2, the cos 90 is 0. Similarly, minus pi by 2, it is 0. So, it will be something like this. Okay, something like this. And when x equal to -1, but it is not touching -1, is not touching. In fact, this point is not attained. Okay. Similarly, this point is not attained. So, but when it is -1 and +1, the value is coming to be -1. So, this is the graph of this function x and this y x. So, value of this is 1. Okay. X y is 1, 0 1, in this is the 0 1 point, and here this point is say -1, here this point is -0 -1. So, cosine of this thing for this function, clearly cosine of pi x always lies between -1 to +1, except for x equal to 0, where the value is cosine 0 is 1. So, when x is different from 0, the value is always -1 to +1, that is mod of cosine x will be less than 1 and there. So, this shows that mod of cosine pi x will remain less than 1 for all x belonging to the interval -1 to 1 minus singleton set 0. This is our question. Hence, limit of this function cosine pi x to the power n when n tends to infinity, this limit will be 0, because this is always be less than 1. So, n is infinity, it goes to 0 for all x belongs to -1 to 1 minus singleton set 0 and equal to 1 for x equal to 0. So, what throughout this function attains the value 0. Okay, function is very smooth function, it is continuous except at the point 0, because what happened this, when you take the left hand limit of this function f x is cosine n to the power pi x, limit of this is f x. So, when you take the f x means 0 minus point, the left hand side point, it means the limit of this thing, limit of cos n pi 0 minus h, just you take the 0 minus h and then here. So, this number will be less than 1 mod of this. So, this will be 0. When you go from the outside, the limit of this the function limit of this function as n tends to infinity, cos of n pi 0 plus h is also 0, that is f of 0 plus, but the value is entirely different from f of 0, because f of 0 is 1. Therefore, 0, their function 0 x equal to 0 is the point of discontinuity, and it is a removable discontinuity. removable discontinuity. That can be easily seen for them, okay, at x equal to 0. So, this is the first kind of discontinuity that is removed. The second type of discontinuity, we call it as a discontinuity of first kind. Discontinuity of first kind, or sometimes we also call the ordinary discontinuity or ordinary discontinuity ordinary discontinuity at this point. Okay. So, what we say is, if the limit exists, both the left hand and right limit exist, but they are different. If a function f x is said to have a discontinuity of first kind at the point x equal to x naught, if limit of this f x when x tends to x naught plus and limit of this f x when x tends to x naught minus, that is right hand limit, and limit exist, both the limit exist, but they are different from have different values. Both exist, but